Sufficient energy now, just in case, I don't think it's likely that you guys will do this, but I sometimes have people say enough sufficient energy. I want you to think about that and think about why enough sufficient energy is a weird thing to say. Why not? Yes. Sufficient means enough. So if you say enough sufficient energy, you're saying enough energy, and that's just weird. Yes, so don't do that. I will laugh at you if you do. Okay. Now, to be fair, I understand, if English is your second language, you might not quite get there, right? Because you're sufficient. It sounds like some type of energy, right? Like not enough potential energy, right? But sufficient means enough. But I have had people, English is their first language, and they have written enough sufficient energy, and I've been like, I'm going to laugh at you, sorry. All right. And we need to have the correct what? Orientation. What's another way of saying orientation? Geometry. Okay. So how many factors are there that affect rate? 6. List them to your partner really quickly. Okay, I'm not going to write them down because they're in your book 17 times, right? Okay. You are also responsible for calculating a rate. Given either a graph or a data table. So what would your formula be for that? Rate is equal to delta amount divided by delta time. And you'll actually write this out. You don't have to write time. You can just write delta t. And then you'll write, whatever you've got. If you want to calculate your deltas before you stick it in the formula, that's also fine. Okay, no worries either way. Let's see. So you do need to show your work. And what should be in the actual work itself? Let's just say this is 3.0, this is 1.0, and this is 10, and this is 0. Units. Yes. If you have found rate in terms of x, whoops, given rate in terms of x, say grams per second, let's say h grams of A, x grams of A, for example, find rate in terms of moles of B per second. Yes? Do you guys know how to do that? Conversion factors, this is just stoichiometry, right? If you have A plus 2B, like obviously you'd need to change grams to moles and then moles to moles. Okay, so you would need to use grams of A to moles of A and then to moles of B, unless you can see there, okay? So things like that where you know that rate is also proportional to the mole ratio. You also need to be able to tell me how to measure the rate of a reaction. So that's the one, that's like 1.1 C, D, C, 1.1 C. So, and I know this one's a little tricky, so tonight your homework's going to be to go home and, you know, do the rest of 1.1C and maybe some of 1.1D, which also has some review in there. Okay? That way you can come in tomorrow and ask questions about that. Okay? What is not on the quiz? Potential energy diagrams, reaction mechanisms. Not on the quiz. We'll have a quiz on that next, shall we say Tuesday? Okay, quiz Tuesday on potential energy diagrams and reaction mechanisms. Yeah? Okay. So this is the quiz that's coming up. Quiz Tuesday on reaction mechanisms, potential energy diagrams, and also kinetic energy diagrams, because we need to finish that as well. Now, if you're feeling overwhelmed by any of this, if you're like, my God, this is going quickly, yes, it is going quickly, feel free to drop by during flex or after school. We can sit down, have a little chill discussion about anything that you would like. We can just go through it. Okay, like I said, this weekend I'm going to try and get those Colger videos like on a playlist so that you can refer to those if you want to as well. And also, if you're interested, that quiz that we are doing is Hebden, the one that's coming up on Friday. This one would be Hebden. So if you're like, Miss Spence, you've been confusing, let's look at Hebden. It is 1.1, 1.2, 1.3, 1.4, and 1.5. Yep. 1.1 to 1.5. So if you're like, I don't have enough questions with the extra practice and the whatever, you know, I've given you, you can go into Hebden and find extra questions. Okay? Yes. Yes. Also, I will be, I don't know if you guys know this, but if I have time, what I've been doing is on Teams, and it's like, here, I'll come back to this in a second if you haven't finished it. If I'm really clever, come on, oh, that's OneNote. I want Teams. Oh no, there is Teams. Okay, there we go. Okay. Homework, what we did in class. Blah, 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 blah. Ooh, look, 2023, 09, 11. It's nothing. Right? So you can just be like, oh, everything's there. That's all the notes that we took on that particular day. Okay? So if I'm clever, I'll put that together for you, like all the sort of, yes. Yes. 1.1 to 1.5 in Hebden can be extra practice, and then there's all the like 1.1b is some extra practice, and 1.2b is some extra practice. Yeah? Hello, yes. Not a problem. So what's going to happen is, you see how this was here with today's thing? I'm going to do that in here. Yeah. 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 No, it's okay. It's like 8.5 by 11 sheet front back. Okay. It's a short-ish quiz. Reaction rates is the shortest, easiest unit of the year. Okay. Now, that does not include spectrophotometry, right? Spectrophotometry is outside of the shortest, easiest unit of the year, right? But yeah, reaction rates is the shortest, easiest unit of the year, which is why I've had you doing some of it more on your own. Last time I taught it, it was like all of a sudden we were semestered and we hadn't been planning on being, and I had it semester 2. And I was like, how am I going to teach everything from, February to May 1st? And so they basically learned all of reaction rates and electrochemistry almost all on their own. We met once a week at lunchtime. And then we reviewed it in class and stuff, but it was not ideal. They did surprisingly well regardless, but yeah. Okay, are we good with that? Shall we finish off reaction mechanisms today? So I think we are on 1.4b, page 91 is where we got to. Oh, I didn't ask, were there questions from the homework? Anything from 88 or 76 to 79? Yes. The graph in the Hebden, okay. That was on like 28, I think, in Hebden, right? Which one is that? What question is it? 50 something? 50 is in equilibrium, so it's not 50. Hang on. No, that's okay. No, that's okay. Hebden, page 28, number 50. There's no graph. Oh, see, you would be confused because that's equilibrium. We have not done that yet. Okay. Any other questions? No. All right. Carrying on then. Okay, each step of a mechanism has its, okay, we're skipping on down to 91. Here we are. So at the bottom of page 91, I would like you to identify the reaction intermediates and catalysts in the following mechanism. Okay, who are our intermediates? HCOOH2 plus and HCO plus. I'll just make those different by putting a box around them. And now we have, who's the catalyst? H plus. Okay, so we now have H plus. Okay, let us just draw a potential energy diagram for the uncatalyzed reaction and then the catalyzed reaction. So here is our uncatalyzed reaction. What goes on the left hand axis? Potential energy. What goes on the bottom? Either reaction coordinate or progress of reaction or anything like that, okay? I tend to go with progress of reaction, but whatever you like. Or reaction proceeds, that's also fine. And I don't know, this is an endothermic reaction. So what should it look like? It is a very, very slow, uncatalyzed reaction. Yes. Yeah, it should be flat for a bit. We should have a very, very big activation energy. And then because it is endothermic, where should we end? Somewhere above, okay? Yes. I'm telling you. There's no way of knowing that unless I tell you. Okay? Yeah. Now, let's draw it for the catalyzed reaction. And in fact, let's draw the catalyzed on here in blue. Let's just draw it on this same axis here. Are we changing the initial potential energy? No, because does a catalyst change the potential energy of the reactants? No. Does a catalyst change the potential energy of the products? No. Now, in our mechanism, in our catalyzed mechanism, how many steps are there? 3. So what should our graph look like instead? We should have 3 bumps. Any thoughts about their height? The second one should be the highest. And what else? They're all lower than that top one. Now, I didn't make a very wide graph, so we're not going to say that this actually represents the time the reaction takes. Okay, but my uncatalyzed reaction would be something like 1, 2, 3. And because I don't know which one of these is faster than the other, it doesn't really matter where I put them, as long as the second peak is the highest, because it is the slow step. The rate, what do we call the slow step? Rate determining step. Excellent. Okay. Alrighty. Carrying on. There's our catalyzed reaction. Just a little review of what a carboxylic acid is. What is a carboxylic acid? It's an acid that ends in COOH And if you recall the what we call the functional group, the carboxylic acid group is the carboxylic acid functional group is this bit here. I always like to think that R stands for the rest of the molecule, okay? Now, what is missing on that? If we were looking at this as a Lewis structure, what is missing on that diagram? Lone pairs. See if you can put on some lone pairs. Who needs lone pairs? Oxygen. So we have this oxygen up here. How many lone pairs does the yellow oxygen need? 2. So there we go. 1 lone pair, another lone pair. How about the blue oxygen? Needs 2 lone pairs. 1, 2. There we go. What kind of bonding would a carboxylic acid be capable of? What type of intermolecular forces? Yep. What type of IMFs can carboxylic acids do? They can H bond. They could, if there was an ion, they could ion dipole. I'm not going to put that, I'm just saying like within itself. London dispersion forces, why? Everything does. London dispersion forces, okay? And also you could have dipole-dipole. If you have H bonding, you can have dipole-dipole. Okay? And don't forget, when a carboxylic acid dissociates, which hydrogen comes off? It's the terminal hydrogen is the one that dissociates. So you're not like, oh, is it one of those H's on the C? No, it's not. It's the H on the O. Why is it that one and not the other ones? Why is it not the blue hydrogens that come off? Have a chat with your neighbor about that. Okay, I'm looking for one particular word in your discussion. Yes, electronegativity. And tell your partner, I know we did it the other day, but tell your partner, what is electronegativity? The ability of an atom to pull bonding I'm going to put stars there because everyone wants to say valence, right? Bonding electrons towards itself. And while we're at it, where do we find the most electronegative and the least electronegative? Top right is the most electronegative, and this is the least electronegative. I would like you to explain why to your partners. Why? They're for my grade 9s. But if I have any left over after school and you would like to come by and take one, you may. Okay, so why are we getting, sorry, Evan, yes. Oh, you're gesturing, you're not raising your hand, yes. Why do we get more electronegative as we go from left to right? Yes? More protons in the nucleus, but we have the same number of, sorry, shielding electrons. And why do we have the same number of shielding electrons? Because we have the same number of shells is correct, but there's a word in there that AP will not be happy if you don't use. Same number of what kind of shells? Occupied shells. So once again, we're going to put little stars beside occupied. Okay. And so we have greater positive charge. Oh, that gives us a greater what? Greater yank. What's the symbol for effective nuclear charge? Z. Yeah? Your effective nuclear charge, because Z is the nuclear charge, the effective nuclear charge is essentially Z minus S, which is the protons minus the shielding electrons. Okay, that's an approximate formula. The real formula is way more complicated than that. And if we have a greater effective nuclear charge, then that means we have what? Greater what? Coulombic attraction, therefore the electrons are pulled in tighter, okay? Okay, so that's why they're getting smaller, and that's why things on the right-hand side of the periodic table are better at attracting electrons towards themselves. All right, where do we have room to write this? Way up at the top, maybe, we could talk about why the trend as we go from top to bottom, why does electronegativity decrease? Tell your partner about that one. Why does electronegativity decrease as we go from top to bottom? I'm not staring, I'm just like into space. Okay, as we go down the periodic table, what's happening? Yes? Okay, so the distance between nucleus, whoops, and bonding electrons increases. Why? Because there are more occupied shells. Where else do we want to go with this? Yes? Yes, yes. So it has to do with the Coulombic attraction because those bonding electrons are further from the nucleus, and we have less Coulombic attraction. Because Coulombic force is inversely proportional to the distance between the charges squared. So that's why. Now, you should, if it looks like it's worth more marks, you should probably also mention that the effective nuclear charge does not change as you go down a group, because although number of protons increases, so does the number of shielding electrons. You can ask an off-topic question. Or have we not already gone off topic? We just go. Yes, absolutely. There's so many balloons because my grade 9s are doing a lab with the balloons this afternoon. We need 30 balloons for a class, and I got 2 classes, and so I haven't blown them all up yet. What we're going to do is we're going to do this. Look. Maybe you guys can predict what will happen. You're going to set up a device like this, and then we're going to snip a little tiny hole in one of them, and the air will leave. I would like you to predict what will happen. Like, let's say that this was the balloon that I snipped the little hole in. What will happen to the balance? Talk amongst yourselves. Are you answering the question, or do you have another question? You have another question, yes? I used to play flute, so I've got good like diaphragm support. But I actually have a blister on my finger now from like the tying them. Yeah, because it's been rubbing. Okay, so if I snip this balloon, what's going to happen to my balance? It's going to tip which away? Is it going to tip towards the left or to the right? It's going to tip towards the right. Why? Okay, you're way more technical than we need to be. Like, it has nothing to do with whether the air is pressurized or not. So if I snip this and this balloon eventually empties, this side is going to go down wide. Lighter or heavier? Doesn't matter. The balloon, we have a balloon and we have a balloon. This is a balloon with air in it. This is a balloon with air in it. Soon there will be a balloon with air in it and a balloon with no air in it. So, which side has more mass attached to the end? The one with the air in it, therefore it will go down because this one will just have balloon, not balloon with air. Yeah. Tricky, right? Now, here's the big problem. This doesn't always work. Like when I have it set up perfectly, it will usually work, but when they do it, like they're not very good at setting it up. So like sometimes it doesn't work for them. But that's why I have one set up already so that we can do it kind of together. Okay. So we were talking about electronegativity, and who is very electronegative? Fluorine, but who else? Oxygen. So what does oxygen do to the electrons in this bond here? It pulls them this way. And what is this oxygen busy doing as well? It's pulling the electrons here, which is also kind of pulling them this. So all the electrons are kind of like, they're being sucked towards the 2 oxygens. And how much density, electron density, does that leave on the hydrogen? Very little, so it's easy for it to just fall off. Okay? Alrighty. Catalyst does not get used up, we all knew that. I would like you to answer on page 93, the questions. Shh. No, that's just pulling within the same molecule. It's just pulling the electron density within that molecule. It's not an intermolecular sort of thing. Yeah. It contributes to the fact that that is a polar molecule, is what it does. Yeah. Give me a wave when you're done. Gotcha. Unless you're just getting good exercise now. Of course. How we doing? We just about ready? Okay, tell me, how many steps in the reaction mechanism? 3. How do you know that? There's 3 peaks. Which one is the rate determining step? Yes. Second one, yes. Now, if we want to show the activation energy of the second step, where would we label that? So we're going to find the activation energy of the second step. Yes. So we're going to end up here. So this is where we're ending. Where would we be starting? Yes. Yes. So this would be activation energy of the second step. If we wanted activation energy of the third step, for example, we could say this is the activation energy of the third step. You don't get called upon to give that kind of information often. Usually, we want to know the activation energy of the overall reaction. Do that one in blue. Oh my God, what's wrong with me? Over, over, all. There we go. Where would I start? Yes. Yeah, we would start from the potential energy of the reactants. And where would we finish? We would finish at the top of the second peak, and that is the activation energy of the overall reaction. And what else do we need to do? We need to label delta H. Yes? Here? Yep. And I would try and make sure that, you know, I make the arrow point upwards. Yes? And that I make it touch each line. So I'm not just like randomly, and then I would label it delta H. We need the axes. What do we label our left-hand axis, y-axis? Potential energy. And what is the unit there? Kilojoules per mole. And how about our x-axis? Progress of reaction, reaction proceeds, whatever you like. Reaction coordinate. Yes. It could point both directions. I have a tendency to always make it go in the direction that it's actually going, so that you can see that, oh, delta H is going to be a positive value because it's going up. Okay? I don't think it's going to be wrong, but you know, I never know on AP exams because, like, I've never marked them. It's this whole big process to become a marker. They call them readers, and I've never gone through the process. So, all right, and what else did it say? It said the axes, oh, the activated complexes. Where do the activated complexes go? At the peaks. Here they are, 1, 2, 3. And where do our intermediates go? In the troughs or in the valleys. Okay, very good. So here is an example, just tidy, nice and tidy, not drawn by me, drawn by someone professional, of a catalyzed and an uncatalyzed reaction. It shows you the activation energy for the various steps. It shows you delta H for both the catalyzed and uncatalyzed is the same. Yes? No. No, it has no relation. Okay? And then, of course, our activation energy for the catalyzed reaction is from the reactants to the highest peak. Okay. If you're not given a catalyzed mechanism and you're told to draw the diagram for a catalyzed mechanism, you can just draw a single peak. If you're told that the mechanism has 4 steps, you're going to draw 4 peaks. If you're told it has 3 steps, you'll draw 3 peaks. But if you're not told how many steps, you can just be like, well, it's going to be lower. And that's all I know about it, so I'm just going to draw it lower. Yes? It usually has multiple steps. I don't know if there's ever a case where it doesn't, because it usually, like goes into a reaction and then it comes out. Maybe when it's a heterogeneous catalyst and it provides a surface on which the reaction can take place. We'll take a little closer look at that later. Okay. I never feel really good about it. I never know what they would ask about it. Okay, there's some questions in Hebden which you can do or not do in the future. Let's see. 1.5a, we're finishing off this unit today. Now, in fact, I think just before we do that, we're going to watch a video here. And then we're going to finish off 1.6a because that's like the extra stuff. I know, right? Full year would be so fan-freaking-tastic. If we could make everybody like who signs up for AP chemistry also sign up for another AP class, we could run them like, but it's really hard because not everybody wants to take the same courses, right? Sorry this is taking so long. You need a little brain break anyway, right? Now, hopefully this whole kinetic energy diagram is easier for you guys because you've already done gases. And it's very, very similar to what gases are about. But let's just, is this on? That's on. Take a little look here, we'll watch this. So these are particles in motion.
This is a graph that describes the behavior of the molecules that we just saw. This is the number of molecules possessing each kinetic energy. Here's low kinetic energy, and here's high kinetic energy, or faster molecules. You notice that there's a few molecules with low kinetic energy, and there's quite a few molecules with medium kinetic energy. And as we move along, there's less molecules with high kinetic energy. So this graph shows the distribution of kinetic energies of the molecules.
So we're good with that? This looks familiar. What do we call this kind of curve? It's a skewed bell curve because you'll notice it's not like this, it's like this, right? Kind of scoops out to the end. Maxwell Boltzmann. Maxwell Boltzmann. So if you haven't done your gases stuff yet, here it is, Maxwell Boltzmann. I dropped a balloon. Oh, that's okay. Thank you. Okay, so here we go.
Now let's review a term we've looked at before, activation energy. Activation energy is the minimum kinetic energy particles must collide with in order to have a successful collision. It's also called the EA. So looking at our kinetic energy distribution, again, the x-axis is the axis for kinetic energy. Let's say that for a particular reaction, this is the activation energy here. What we can do is we can draw a vertical line through this graph and call it EA. Each point on this line gives the number of molecules with each kinetic energy. So for example, there's this many molecules that possess this amount of kinetic energy. The total number of molecules with a certain range of kinetic energies can be found by taking the total area under the curve for that interval. For example, let's consider the interval of the molecules with kinetic energy greater than or equal to the activation energy.
Okay, where would we shade this to show the total number of molecules with kinetic energy greater than EA, the activation energy? To the right.
Energy EA. That would be represented by this interval here. So the shaded region, the area under the curve here in this interval, represents the total number of molecules with kinetic energy greater than or equal to EA.
What would represent all the molecules? The total number of molecules all together. Their area under the whole curve. Can you see how now we can sort of start maybe predicting what percentage of collisions will have enough energy, right? We're going to be approximating a little bit, but we can sort of look at the diagram and figure it out. Here we go.
The total area under the curve represents the total population of the molecules in the sample. Let's say we want to find the fraction of molecules in the particular sample that have kinetic energy greater than or equal to EA. So what we could do is we can estimate how many of these little triangles would fit under the whole curve that represents the total area. So with a little imagination, we can see that there's about 20 of these that will fit under the whole curve.
Isn't that nice that he's made all those little triangles for us, all about the same size? So there's about 20 of them.
So about 1 in 20 of the molecules have kinetic energy greater than or equal to EA, or about 1/20 of the molecules have sufficient kinetic energy for a successful collision. Because there's only 1/20th of the molecules that have sufficient energy, do you think this reaction will be fast or slow?
Fast or slow? Slow, yes. I think you're like, I think it's like, I mean, honestly, when they say number of molecules, they're really talking about like the number of collisions. So it's the energy of the collision rather than the energy of the actual molecules themselves. Does that make sense? Yeah, okay.
Well, it would probably be slow. So what happens to this distribution if the temperature is increased?
What happens to that distribution if the temperature is increased? Tell your partner. Okay, there's a few things that are going to happen here. What's one of the things that's going to happen? You guys always answer. I want other people to start answering questions. Yes, Alvin. It'll do that. Okay, so is it going to then look like this? Ah, it stretches. Okay, so let's get rid of this. Dropping my pen. Like that? Tell your partner, do you like my second graph or not? No. Yes. Yeah, it needs to be flatter because the number of particles is staying the same. I have increased the area right now, yes? So yeah, it needs to get flatter. Okay? It won't actually touch zero. It goes, how does it go towards zero? It goes asymptotically. Oh, I love that word.
Let's have a look at the model. When the temperature is increased, we haven't added or taken away any molecules. So what do you think will happen to the total area under the curve?
Has to stay the same. We just talked
It'll
about
stay the
that.
same. But
Will we have more or less slow molecules? Less.
do we have more or less slow molecules now? Well, you can see we have less slow molecules. Do we have more or less fast molecules? Well, we have more fast molecules. So the kinetic energy graph does the following. So at a higher temperature, indicated by the red curve, you see we have less slow molecules, and we have more fast molecules. We notice that the whole curve
Yes. Well, it's the number of molecules, it's the energy of the molecules. Just go with molecules. Okay? Depending on the context. Whatever makes it easier for us. Yes? Yes.
curve has moved toward the right and flattened out a bit. But the total area under the curve remains the same. Now let's put the activation energy, EA, in again.
So what has happened to the fraction of collisions with sufficient energy? It's increased because the area under the curve there is greater.
This interval here represents the molecules with kinetic energy greater than or equal to EA at the lower temperature. So this triangle here represents all of the molecules with kinetic energy greater than or equal to EA for the lower temperature. Let's see what happens with the higher temperature. Here is the interval for the molecules with kinetic energy greater than or equal to EA for the higher temperature. So this triangle represents the molecules with kinetic energy greater than or equal to EA at the higher temperature. You'll see that when the temperature is increased,
What would happen to the EA line if we added a catalyst? Activation energy line. What would happen to it if we added a catalyst? Tell your partner. So the activation energy will move to the left. Therefore, what will happen to the percentage of collisions which are effective? It will increase, yes. Okay, that's basically it. Your homework is to do review of sections 1.1 and 1.2. So you're going to go through, you're going to, like, you know how you did all the even or odd questions? You might try the even ones. You can do the ones that say extra practice. Okay? So homework is study for your quiz. That way, if you have questions, you can ask me tomorrow. Find it last night, and I couldn't remember ever having. I got 2 blocks. I need 30 per block.
Well, what is that for?
It's for a lab where they're going to set it up like that, and then we're going to snip one of the glues so that the air slowly releases, and they have to predict what's going to happen and see what's going to happen.
Oh, you're actually and the
Well, normally in the past, Mr. Wolf has had a balloon blower that I use, but we can find it this morning. So yeah, super fun times. Yes. They can't do it because they suck. No, I'm serious. Like they cannot blow the balloon, they cannot hide the balloon. Like they kind of
blowing balloon requires skill though. I'm not gonna lie.
like it makes me actually laugh a little bit because I'm like, yeah, what? Right? But yeah, they're like, I can't blow it up. And then they can't fly it. Like I have to teach my son how to fly a balloon. Right? He's like, I can't do it. And I'm like, do it like this. And
The tying is the hardest. No, the blowing is the hardest
you
part.
have small fingers. I go around both, and then I have a nice little space for the other. You've got really big fingers.
Yeah.